Okay, this screencast is talking about the dnorm function in R. In words, what the dnorm function does is this. We've got our nice Gaussian distribution here, Gaussian or normal distribution, and at any distance from 0, that's x equals 0 there, but at x equals 0 here, but at a distance x from there, dnorm x gives me that distance there, that vertical distance. So it starts out at a maximum height here at 0, then it gets smaller symmetrically because it's symmetrical positive and negative. Smaller, 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 never actually falling to 0. It's a bit difficult to draw. It never actually falls to 0. It just gets smaller and smaller and smaller as you get further and further away from x equals 0. So I guess I should set up coordinates x and y like that. Okay, so let's have a look at it in R. Here's R. And as ever, the first thing to do is question mark dnorm. And we see here it's the help page. R norm is covered before. Here's dnorm. I'm not going to cover this final log argument here, but I'll cover these other arguments here. So dnorm x, and x is the horizontal distance along the horizontal axis there. So that's dnorm, and it gives us the density of the Gaussian distribution. So let's just try it. Here's my R window, and we'll have a look at it. If I say x becomes a sequence from equals, let's say, -4 to equals 4, length equals 100, and if I just type x there, I'll just make that a bit bigger. I'll just do that again. That's my command. X equals a sequence from -4 to 4, length 100. And if I type, so that's x, type x again. Oh, you can see it all because I've made the window bigger. There's the first element from -4, so you see it can start at -4. That's element 99, that's element 100, which is 4, because I told it to start at -4, from -4 to 4, and 100 long. So that's the 100th element. Now what I want to do is to use dnorm with that value of x there. So I'll just bring this up here. I'm going to go plot x, dnorm x. And we can see this Gaussian shape, this beautiful Gaussian figure here emerging out of our calculations. There it is. And this is like the histogram that we saw before. If I go hist R norm of, let's say, a large number of observations, let's give it a few more zeros, we see a sort of numerical lumpy bumpy random version. But this value here, this dnorm x, gives us the perfect mathematical formulation, the perfect density function for the Gaussian. Isn't that beautiful? Alright, what I want to do now is to show you how I can use the other... Ooh, it's not that one. I wanted to show this one here. To show the other arguments. So we've got x, which is the horizontal distance. Now I want to fool around with the mean and the standard deviation. And you can see from here, just the same with R norm. The mean is 0 and the standard deviation equals 1, unless you override that by telling R that you want to use a particular value. So you can try that. I can go plot x, dnorm, but I'll say a mean equals, let's say, 0.5. And you can see how it's moved it across there. The trouble with this is that once I use my plot statement there, if I do another plot statement, what it does, it says, he wants a new graph, so it sets up new axes and new everything. And you lose the original picture. To get both on the screen at the same time, just hit the up arrow here to get back to that command. That's my standard case with a mean of 0 and a standard deviation of 1. If instead of plot, if I go points, then what this points command... What this points... Oh, I've done it again. What this points command here does, it doesn't set up a new plot, it just puts the points on the existing plot. Oh, there we go. So you can see them both at the same time. That's the original one, and that's got a mean of 0.5, which is down here. And I can put more and more on. I can say a mean of, let's say, 1.5, and it's put this guy on here. Let's just go back to the standard case. There it is. So because I've used the plot command, it starts again and we've got the nice fresh ones. Let's go that, and then I can say colour equals red, and then we can say which one's which. So that's got a mean of 1.5, which is here, and indeed I can show you that by going AB line vertical at 1.5. AB line vertical at 1.5, and then we'll see, oh there we go, that's 1.5. You see it's between 0 and 2, so that's showing us the mean of the red points there. So we can shift the mean left and right as we wish. Let's try mean equals, let's try minus 2. And I don't want to use red again. I'm having a little bit of difficulty keeping everything. I'll just make that, there we go. So I'll make it, let's say, blue. There we go, and we can see this beautiful Gaussian picture over the left, a mean of minus 2 there. So we can slide the mean around left and right as we wish. What I'm going to do now, if I go $dnorm again, oh, incidentally, you see I'm just casually, you see how I'm just casually using these points and AB line functions. If you want to know more about this AB line thing, just go $AB line, and it fires up the help page for AB line, which is all this stuff here. But we've still got the original help page there for rnorm. So you can get help on anything by going ? What I'm going to do is go back to the default case, x dnorm of x, and that's what we started with. What I'm going to do now is to change the standard deviation argument on, oh no, it's this one, isn't it? Change the standard deviation argument. So let's have a look at that. Find the R window, which is here. So I'm going to plot dnorm x, comma, standard deviation equals, well, standard deviation equals 1 is the default, but if I go standard deviation equals 2, oh, I meant to say points. That's plot, there's plot again, so that's why I lost the original command. If I go points, here we go. What's happened here is that there's the standard mean 0, standard deviation equals 1. This one is showing a wider standard deviation. It's a wider picture, a wider distribution, because we've set the standard deviation twice as wide. So it should be twice, the distribution should be twice as wide. And two things have happened. Yes, it's got wider, but it's also got lower because it's got to maintain the total area equal to 1. And so we can see that it's lost area here and here, but gained it here. I'll do that again. Let's try that, and then I'll say colour equals red, just so we can see which one's which. You can see something else has happened with a standard deviation of 2. You see, I've not quite, -4 isn't low enough because we've still got quite a lot of probability on the red curve, at least, out here and out here. So when I defined x, I should have gone a little bit further, and I'll do that now. X becomes a sequence from equals, let's say, -7, 2 equals 7, length equals 100 again. Plot x dnorm x, oops, gives me that, and then I'll go to this one here, and then we can see all of this curve, which is quite nice, beautiful. Oops, I don't know why it does that. I'm not. It's done it again. Okay, now I can also make the standard deviation, let's do a blue one here, make standard deviation smaller. I can make it 0.7, let's say. Now what's happened here, there's the blue points there, it's squashed it out right up here. The curve would carry on going up there, but it's because I'm plotting the points and not rescaling the axes, it's just omitting to plot these points above the axis here. To get those as well, what I can do is go back to the original one there, but I can specify the y limits of 0 and, well, how high is this one? This one's 0.4, so we'll go up to 1. Let's try 1. Oh, here we go, sorry. 1. There we go. And because we're going all the way up to 1 here, we can see it looks a little bit squashed. So now I can go and do this one here with a standard deviation of 0.7, and we see all of it. And indeed, I can take the standard deviation down even smaller, let's say 0.4, and we can see this picture here. And there's no reason why I can't play with both of them at the same time. Red, both of the arguments, and make the mean equals 1, let's say. So here we've got a standard deviation of 0.4 and a mean of 1. We can see these red curves here going down there. Oops, I'm having difficulty controlling this. I'll just go back. Let's go back to our old one. Plot x dnorm of x, and we can see. You see, it's used this. It's scaled it automatically because I've not given it a ylim argument to scale the plot. We can see that the value at 0 is the maximum that it gets. In fact, if I put a grid on it, we might be able to see it a bit better. Yeah, here we go. You can see it takes the value at 0 is 0.4, just a tiny, tiny bit under 0.4. So we'll just verify that. dnorm 0, and it should be about 0.4. Oh, look, it's 0.398. So that's pretty good. It's actually 1 over the square root of 2 times pi, if you want the accurate value, which is that. But yeah, you can take that or leave it, I guess. Let's just do one more validity. The reason I want to do this is that I want to just check that this curve here, or this line, this set of points I've plotted here, corresponds to reality. It's just like a reality check. So if I go dnorm of 0, I say it's 0.4, and it is. So what that means is that I've just checked that my understanding's correct here. I'll just do one more and then I'll stop. Let's try the value at -2, and that comes out to this value here, which is about, looks like about 0.05, doesn't it? So let's try dnorm of -2, and it should be about 0.05. Oh, look at that, 0.053 something. So that's not bad. There's just one more thing I want to check. We can see by eye that this curve is symmetrical, and if you look at the equation for it, for the density, you can see that it is exactly symmetrical. So that tells us that dnorm of +2 should be the same as dnorm of -2. So let's have a look at that. So there's dnorm of 2, and it should be the same value. And it is, because that agrees like that. Well, that's wonderful. Yeah, I think that's great. Actually, I'm just going to do one more thing. Let's say 100. Now, dnorm of 100, you see this axis here, 0, 2, actually, let's pull that in range there. 2, 4, 6, 100 is going to be like yards and yards and yards away. It's going to be miles away to my right. But what you should know is that dnorm of 100 should be almost 0, because this curve has been flying down towards 0, and it's getting very, very, very small. So dnorm of 100 should be infinitesimally small. There you go, and it comes out to be exactly 0. Okay, there's dnorm. I'm going to stop there.